So you can see as the wind is taking away water from this side of the fish tank, the water is now coming up from the bottom to fill that gap, and that's what is upwelling. In the real world, we have a lot of places where upwelling happens. The African coast, western side of the Africa, western side of northern Africa, some parts of Asia, and then the Peru coast, the American coast, North American coast, and also the equatorial region where also the winds influence the upwelling there. So these are the regions where you have strong upwelling that influence both climate as well as the ecosystem, because when you have upwelling, the water is bringing nutrient rich water from the subsurface to the surface. That's why it is the most effective region for primary productivity. Like we see a lot of phytoplankton there, and then the chain of ecosystem from phytoplankton to zooplankton to small fish to big fish, and that's how these regions are rich in biodiversity and ecosystem. Now this is a cross section. If you take on the equator from surface to about 1,000 meter, and then this is the African coast, the American coast, and the Indonesian coast here, and the African coast again there. So you can see that in all the basins, the eastern side of the basins are like cooler. The temperature is upwelled, so the thermocline, what we call this as a thermocline, this line is tilted upward to the eastern side. Indian Ocean is slightly different because I told you we have monsoons, so summer and winter are different for the Indian Ocean. So basically this tilt in the temperature in the subsurface, like around 200 to 100 meter, that tilt is determining how we get the El Nino Southern Oscillation and the Atlantic Nino Nina, which I'm not going to cover today. So I told you we have several hypotheses that explains the El Nino Southern Oscillation phenomena, the Earth's interactions. And Bjerknes feedback is one of the oldest hypotheses. What it says that because the wind is blowing from east to west in the Pacific equatorial region, and as you see, the deflection because of the Coriolis effect is causing upwelling, and that upwelling is kind of causing cool water at the surface on the eastern side, and the water transported away from the eastern side accumulate on the western side, so we have warm temperature there. And this east-west gradient, cool temperature on the east, warm temperature on the west, helps the wind actually, because the wind blow from cool temperature to warm temperature, so this side is cold, that side is warm. So wind continues to blow from east to west in the tropical Pacific, and as wind accumulate on the Indonesian side, they converge and rise up. When wind rise up, they take moisture with it, and when moisture is going from higher temperature at the surface to lower temperature as you go above the surface, they condense and we get the cloud and the rainfall on that side. On the top of troposphere, we get the air when rising will give away all the moisture, and it is dry there. So dry air then diverges from the western side of the Pacific, from the Indonesian side to the American side. So the wind blow from west to east in the tropical Pacific, and then sink near the American coast, and then feed back to the surface wind. So this circulation is called the Walker circulation in the atmosphere, and the SST gradient is supporting that through the surface wind because of the east-west SST gradient. The winds are sustained, and that's how the SST, the wind, and the Walker circulation will maintain this kind of normal state in the tropical Pacific. So usually eastern side is cold, western side is warm. We have more rainfall on the Indonesian side, drier condition on the American side, and that's how the system operates. Now sometimes the wind blow from west to east, from the Indonesian side to the American, South American side or North American side, to the American coast. And that happens unusually once in 2 years or 5 years, sometimes 7 years. And that is the situation we call the El Nino conditions. because now wind is blowing from the west side to the east side. So the water is driven away from the western side, and they are moving to the eastern side. So eastern side is warm now. This side water is accumulating, so the American coast is warm, whereas the Indonesian coast is cold. That's why the wind will drive away the moisture from the Indonesian region and will accumulate on the eastern side, the American coast side. So now the rainfall will be on the eastern side of the Pacific, not on the western side. And then the rising air will eventually diverge from the American coast to the Indonesian coast to complete what we call the anomalous Walker circulation, because this is normal, this is anomalous situation. So that's why it is called anomalous Walker circulation. So this anomalous Walker circulation will be again maintained by the SST gradient. West is cold, east is warm, so winds are coming from west to east, and the Walker circulation is maintained because of the rainfall here and the divergence of the wind in the upper troposphere. And that completes the cycle of how SST gradient and the wind, surface wind, and the Walker circulation will maintain the El Nino conditions. La Nina condition is the kind of stronger normal condition when the winds are stronger from the east to west. Eastern side is very cold, western side is very warm. So this is a stronger situation compared to normal conditions. So that's what is La Nina. El Nino is exactly opposite of these two situations, normal and La Nina. La Nina is a stronger condition of normal situations. So that's the Bjerknes feedback. As you can see, it is explaining the three phases of El Nino: the normal situation, the stronger La Nina situation, and the opposite El Nino situation. So these are the three states, and Bjerknes hypothesis given by Bjerknes is explaining those three states. But if you are careful, you can see that this theory is not explaining why the situation will change from this state to this state, and from this state to this state, or this state to this state. And that transition is to some extent explained by other hypotheses. The hypothesis by Urki, who says that the Pacific warm water builds up, and once it reaches a critical value, then it releases the warm water to the eastern side of the Pacific, and then El Nino happens. And once everything is discharged, all the warm water is discharged, then the cool state happens, and that leads to La Nina. So the red line here is showing you the depth of 20 degrees centigrade isotherm. So the depth up to what the temperature in the subsurface is 20 degrees centigrade. Usually western side is higher depth because all the water is accumulating on the western side. And if you take the average, you can see that before an El Nino happened, like in 1982, before it happened, the warm water volume was very high, and then it releases to the eastern side. The El Nino happened. Once it releases the heat, the warm water volume now decreases to lower values, and that leads to La Nina. Then again the warm water volume builds up, and that leads to the next El Nino and discharge. So then again low volume of high water volume and warm water volume, and then we have the La Nina, and then gradual build up El Nino, and that's how this thing happens. So this theory to some extent explains why you have a transition between El Nino and La Nina. Now there are other hypotheses. This one is explaining, but this one is not helping us to understand the dynamics and also to help us in predictions. So the next theory given by McCreary is explaining that through what we call the ocean dynamics. So usually, as you have seen my previous slide, the winds are from trade winds are from northeast to southwest, and that kind of wind helps deepening of thermocline of equatorial regions like 5 to 10 degrees north and 5 to 10 degrees south in the western Pacific. And that high thermocline depth can propagate westward as Rossby waves. Rossby wave usually propagate from east to west. So the high volume of water, warm temperature, move westward because of the Rossby waves, and then the Rossby wave deflect on the Philippine coast and the Indonesian coast and reach the equator as coastal Kelvin wave. So Kelvin wave needs a boundary to the left in southern hemisphere and to the right in the northern hemisphere. So when the Rossby wave reach the coast, they kind of converted into Kelvin waves, and the Kelvin wave, when they reach equator, they propagate back. So you can see the Rossby wave now reaching the coast and turning to Kelvin waves, and then reach the equator, and then at the equator the Kelvin wave finds the wall on both sides. So that's why they propagate from west to east as warm Kelvin wave, because these are warm motors. So they bring one motor to the eastern side as Kelvin wave, and they reach the eastern side as warm Kelvin wave. The El Nino sets in, and by that time winds are reversed. So they are now producing upwelling. So that upwelling water is cold, and they are again propagating to the Indonesian and Philippine coast as Rossby waves. Reach the coast, then turn to Kelvin wave. Now Kelvin wave is cold Kelvin wave. It propagates to the east, and then we have the La Nina situation. So this is the kind of wave dynamics which explains why we can have the El Nino, La Nina, because of the wave dynamics, air-sea interactions, the thermocline depth, the Ekman pumping. All those explains this kind of ocean dynamics, ocean atmosphere dynamics, to explain the El Nino. But the only issue is that these are waves which take like 1 year to cover on the east-west. So we should have El Nino, La Nina every 1 year, and that doesn't happen. We don't have regularity in the El Nino, La Nina cycle. We have a periodicity, not periodic El Nino and La Nina. So that aperiodicity cannot be explained by this theory. Nevertheless, it explains how the phenomena happens through the wave dynamics. Stop here. Yeah, okay.